Weather Satellites Introduction Welcome, listeners, to a journey above the clouds, into the realm of satellites that silently orbit Earth and watch over our weather. Every day, we check our phones or watch the news to see tomorrow's forecast. Will it rain? Will there be a storm? Will the skies be clear for travel? These answers don't just come from weather stations on the ground. They come from hundreds of kilometers above, where powerful weather satellites orbit Earth, continuously observing our planet's atmosphere, oceans, and land. Weather is not just about carrying an umbrella or planning a picnic. It shapes our lives, our economies, and even our safety. A single storm can affect millions, a hurricane can reshape coastlines, and droughts can change entire regions. Without satellites, predicting these events with accuracy would be nearly impossible. Today, we'll dive into the fascinating world of weather satellites. From the United States' Advanced GEOS series, Europe's reliable Meteosat program, Japan's cutting-edge Himawari satellites, to the USA's polar-orbiting NOAA satellites, we will uncover how these space-based guardians track storms, monitor climate change, and help us prepare for natural disasters. The origins of weather satellites. To understand the weather satellites we have today, we need to travel back to the dawn of the space age. In the 1950s and early 1960s, meteorology faced a huge limitation. Weather forecasts were made using balloons, airplanes, and ground-based instruments. These tools could only measure conditions locally. They gave us fragments of the big picture. But Earth's weather system is global. Storms don't stop at borders, and hurricanes don't respect coastlines. Humanity needed a way to watch the entire planet's atmosphere at once. That breakthrough came in 1960, when the United States launched TIROS-1, the first weather satellite. TIROS stood for Television Infrared Observation Satellite. It was small, only about 42 inches wide, shaped like a drum, with 2 television cameras on board. And yet, it changed meteorology forever. For the very first time, scientists could look down from space and see the swirling clouds of Earth. The black and white images may seem simple today, but in 1960, they were revolutionary. Suddenly, forecasters could watch the development of storms in real time, rather than waiting for scattered ground reports. Throughout the 1960s and 1970s, new satellites quickly followed. The United States launched more TIROS satellites and then developed the SSA and Nimbus series, each more advanced than the last. These satellites gave longer coverage, higher resolution images, and infrared sensors that could see clouds, even at night. Meanwhile, the Soviet Union also developed its own weather satellites, contributing to a new era of global meteorology. For the first time, nations began sharing satellite data, because weather, after all, is a universal challenge. The 1970s introduced 2 major breakthroughs: geostationary satellites and polar orbiting satellites. Geostationary satellites orbit the Earth at the same speed that Earth rotates, staying fixed over one region. This means they can continuously watch the same area, perfect for tracking hurricanes or thunderstorms in real time. Polar orbiting satellites, on the other hand, circle Earth from pole to pole, scanning the entire planet as Earth rotates beneath them. They provide global coverage, capturing detailed snapshots of the atmosphere and surface, twice each day. These 2 types of orbits, geostationary and polar, became the foundation of modern weather observation. By the late 20th century, weather satellites had gone from simple cloud cameras to sophisticated machines capable of measuring temperature, humidity, wind speed, sea surface conditions, and even ozone levels. They were no longer just tools for daily forecasts. They had become essential for disaster preparedness, aviation safety, and climate research. The launch of TIROS-1 in 1960 marked the birth of space-based weather monitoring, and every satellite since then has built upon its legacy. From those grainy black and white images to today's colorful high-resolution scans, weather satellites have transformed how humanity understands and predicts the forces of nature. Asterisk. GOES Series America's Weather Watchers asterisk. As the space age advanced, the United States invested heavily in satellites that could provide constant, uninterrupted weather coverage. This gave birth to one of the most important satellite programs in history, GOES, the Geostationary Operational Environmental Satellites. The concept was simple, but brilliant. Place a satellite in a geostationary orbit, minus 35,786 kilometers, above Earth, where it circles the planet at the same speed that Earth rotates. From that vantage point, the satellite appears to hover over one fixed region, like a watchful guardian in the sky. This allows meteorologists to monitor weather systems in real time, 24 hours a day. The first GOES satellite was launched in 1975, and over the decades, the program has evolved into one of the most advanced weather monitoring systems in the world. Let's look at the latest generation, GOES 16, GOES 17, and GOES 16. GOES 16, the East Coast Guardian, launched in 2016. GOES 16 is also known as GOES. It keeps constant watch over the eastern United States, the Atlantic Ocean, and South America. At the heart of GOES 16 is its Advanced Baseline Imager, or ABI. This instrument can scan the Earth in 16 spectral bands from visible light to infrared, giving scientists the ability to see clouds, smoke, ash, dust, and even subtle temperature differences in the atmosphere. The ABI can take images of the entire Earth every 15 minutes, the continental US every 5 minutes, and special storm regions every 30 seconds. This rapid-fire imaging has revolutionized hurricane tracking. For example, during Hurricane Harvey in 2017, GOES 16 provided forecasters with detailed, near real-time data, helping emergency teams prepare and respond. It also monitors wildfires, detecting hotspots before flames are even visible from the ground. This gives firefighters precious time to act. GOES 17, watching the West 2 years later, in 2018, GOES 17 was launched. Positioned as GOE, it monitors the western United States, Alaska, Hawaii, and the vast Pacific Ocean. However, shortly after deployment, engineers discovered a cooling system malfunction in its infrared sensor. This limited its ability to capture certain thermal images during parts of the day. But even with this setback, GOES 17 remained invaluable. It continued to track Pacific hurricanes, volcanic eruptions, and wildfires across California and the western states. Its data, combined with GOES 16, provided a nearly complete picture of weather across the Americas. GOES 18, the replacement and upgrade to ensure reliability. GOES 18 was launched in 2022 as a replacement, an upgrade for GOES 17, with a fully functional cooling system. GOES 18 restored complete coverage over the Pacific and western U.S. together. GOES 16 and GOES 18 now form a powerful duo, one watching the east, the other watching the west. From their vantage points in space, they cover nearly half of the globe, providing uninterrupted streams of data. Beyond images, lightning, space weather, and more. But GOES satellites are more than just weather imagers. They carry instruments that detect lightning activity across entire continents. This helps meteorologists spot severe thunderstorms before they intensify. They also monitor space weather, solar flares, radiation storms, and geomagnetic activity that can disrupt satellites, GPS, and even power grids on Earth. Real-world impact. The impact of GOES satellites on human safety is profound. During the 2018 California wildfires, GOES data helped pinpoint ignition points and track smoke plumes. In hurricane season, GOES imagery allows forecasters to issue life-saving evacuation warnings days in advance. Aviation and shipping industries rely on GOES for real-time storm tracking, avoiding dangerous conditions. In many ways, GOES satellites are the eyes of America's skies, silently watching, recording, and sending back streams of information that touch millions of lives every day. Meteosat series, Europe's Guardian *. While the United States was building its GOES fleet, Europe also recognized the importance of space-based weather monitoring. In the late 1970s, European nations came together to create their own satellite program, one that would not only protect Europe, but also support weather prediction across Africa, the Middle East, and beyond. This collaboration gave birth to the Meteosat series, operated by EUMETSAT, the European Organization for the Exploitation of Meteorological Satellites, the first Meteosat, 1977. The very first Meteosat satellite was launched in 1977. Like the American GOES satellites, Meteosat was placed in a geostationary orbit, hovering above the equator at 36,000 kilometers. From this position, it could provide continuous views of Europe, Africa, and the surrounding oceans. For the first time, European meteorologists had direct real-time access to satellite imagery. This dramatically improved the accuracy of forecasts, particularly for severe storms, floods, and winter weather. Meteosat second generation MSG. By the early 2000s, technology had advanced, and so had the Meteosat program. The second generation Meteosats, known as MSG, were launched. Starting with Meteosat in 2002, these satellites introduced Severi Imager, the spinning enhanced visible and infrared imager, with 12 spectral channels. Severi could detect fine details in cloud patterns, dust storms, volcanic ash, and even fog forming at night. The MSG satellites could send images of the full Earth disk every 15 minutes, a huge leap forward for operational meteorology. Airlines, shipping companies, and national weather services relied heavily on this rapid data flow. Meteosat third generation MTG. Today, Europe is moving into an even more advanced era with the Meteosat third generation, or MTG. The first MTG satellite was launched in December 2022. This new generation doesn't just provide sharper images, it includes revolutionary instruments, a lightning image capable of detecting lightning strikes across Europe and Africa, both day and night, an infrared sounder, which can measure temperature and humidity throughout the atmosphere with great precision. With these tools, MTG can improve storm warnings, track extreme weather events, and even enhance climate monitoring. Impact on Europe, Africa, and beyond. Meteosat is more than just a European asset. Because of its orbital position, it provides crucial data for Africa, where ground-based weather stations are often scarce. This information is vital for predicting droughts, floods, and monsoon patterns that affect millions of people. For Europe, Meteosat data is essential in forecasting powerful Atlantic storms that sweep across the continent, sometimes causing widespread flooding and damage. The aviation industry also depends on Meteosat for safe transcontinental flights. A true guardian, the Meteosat program shows how international cooperation can save lives. With each generation, the satellites have become more accurate, faster, and more advanced. Together, they form the backbone of Europe's weather prediction system, a guardian watching over 2 continents and countless lives. Himawari Simbilan. Japan's weather eye. As Europe advanced its Meteosat program, Japan was building its own powerful fleet of weather satellites, designed to watch over the vast Pacific Ocean, a region where some of the world's strongest storms are born. These satellites are known as Himawari, a Japanese word meaning sunflower, a fitting name. Since the satellites gaze constantly toward Earth, much like a flower turns toward the sun, the Himawari legacy. Japan's first Himawari satellite, launched in 1977, around the same time as Europe's first Since then, The series has evolved into some of the most advanced weather satellites in the world. In recent years, two satellites have stood out. Himawari 8 and Himawari 8 launched in 2014. Himawari 9 followed in 2016. Together, they provide continuous coverage of the Asia-Pacific region, including Japan, Southeast Asia, Australia, and the Pacific Islands. Himawari 8 and Himawari 9 technology. Both satellites carry a 16-band imaging instrument, capable of observing the Earth in visible light, infrared, and near-infrared wavelengths. This means they can capture details ranging from storm clouds to volcanic ash, and even find dust in the atmosphere, unlike older satellites that delivered updates every 30 minutes. Himawari satellites can send a full Earth image every 10 minutes, and in rapid scan mode, specific regions can be imaged every 2.5 minutes. This speed is critical in regions where typhoons form quickly and change direction without warning. Life-saving role in disasters. The Himawari satellites have proven their worth many times. During the 2015 Typhoon Soudler and later Typhoon Hagibis in 2019, Himawari provided real-time tracking that helped governments issue timely evacuation orders. In January 2022, when the underwater volcano erupted near Tonga, Himawari 8 captured stunning images of the explosion and the massive shock waves spreading across the atmosphere. These images were not only historic, but also vital for issuing tsunami warnings across the Pacific. International cooperation. What makes Himawari truly special is that its data isn't just for Japan. The Japan Meteorological Agency, JMA, shares the satellite's data with other countries, including Australia, New Zealand, Pacific Island nations, and even the United States. This global sharing ensures that the entire Asia-Pacific region benefits from accurate, timely forecasts. 4 countries vulnerable to typhoons, cyclones, and tsunamis. Himawari satellites are not just tools, they are lifelines. A constant watcher in the East. The Himawari 9, like its predecessor, will continue operating well into the 2030s, ensuring that Japan and its neighbors remain under constant watch. With their rapid imaging, broad coverage, and international data sharing, the Himawari satellites have set a gold standard in regional weather monitoring. NOAA 20, America's polar orbiting weather satellite. So far, we've explored geostationary satellites like GOES, Meteosat, and Himawari. These satellites hover over one fixed spot, watching the same region day and night. But what if you need to see the entire Earth, every continent, every ocean, every storm system? For that, we need a different kind of satellite, the polar orbiting satellite. Polar orbiting satellites, how they work instead of hovering. A polar orbiting satellite circles Earth from pole to pole at an altitude of about 800 kilometers. As the Earth spins beneath it, the satellite scans different slices of the planet on each orbit. Within 12 hours, it has mapped the entire globe. This is where NOAA-20 comes in. NOAA-20 and the JPSS program launched in November 2017. NOAA-20 is part of the Joint Polar Satellite System, or JPSS, a partnership between NOAA, the U.S. National, Oceanic and Atmospheric Administration and NASA. NOAA-20 is sometimes called the most advanced weather satellite ever launched into a polar orbit. Its instruments provide scientists with data not just about weather, but also about long-term climate patterns. Instruments on board: NOAA-20 VIIRS, Visible Infrared Imaging Radiometer Suite, produces high-resolution images of Earth's surface and atmosphere. It can detect snow cover, ice, wildfires, and even the glow of city lights at night. CR's Crosstrack Infrared Sounder measures temperature and moisture at different layers of the atmosphere, giving meteorologists a 3D profile of weather systems. ATM's Advanced Technology Microwave Sounder looks through clouds to measure rainfall, humidity, and storm structure. OMPS Ozone Mapping and Profiler Suite monitors the health of the ozone layer and tracks ultraviolet radiation levels together. These instruments provide a complete picture of Earth's weather and climate systems. Real-world applications. NITNIS data has countless applications. Hurricane forecasting by measuring ocean surface temperatures and atmospheric conditions. NOAA 20 helps predict how strong a storm will become. Climate change research. The satellite tracks melting sea ice in the Arctic, shifts in snow cover, and long-term temperature changes. Disaster response after major floods, wildfires, or volcanic eruptions. NOAA 20 images help governments assess damage quickly. Everyday forecasts. The data from NOAA 20 feeds directly into the weather models that power the forecasts we see on TV and smartphone apps. A global perspective. Unlike geostationary satellites that focus on one region, NOAA 20's polar orbit gives us a truly global view. From the Amazon rainforest to the Sahara Desert, from the Arctic ice caps to the vast Pacific Ocean, NOAA-20 records it all. It works in tandem with geostationary satellites like GOES, while GOES watches storms develop in real time. NOAA 20 provides the bigger picture, ensuring no part of the Earth is left unseen. A silent sentinel, OAA 20, is a reminder that weather prediction is not just about technology, it's about safeguarding human life. Whether warning of hurricanes, tracking climate change, or monitoring the fragile ozone layer, NOAA-20 plays a critical role in keeping humanity prepared. How weather satellites help us every day. We've learned about GOES, Meteosat, Himawari, and NOAA-20. Each has unique technology and missions, but together they form a global network of silent guardians in orbit. But what does all this mean for you and me in our daily lives? The truth is, weather satellites shape nearly every aspect of modern society, often without us even realizing it. Saving lives in severe storms. One of the most important roles of weather satellites is disaster prediction and preparedness. When a hurricane forms in the Atlantic, satellites like GOES-16 track its path, intensity, and speed, giving governments days to prepare evacuation plans. In the Pacific, Himawari 9 keeps watch over typhoons, ensuring island nations like the Philippines and Japan have enough warning before landfall. In Africa and Europe, Meteosat satellites monitor thunderstorms and heavy rainfall that can cause flash floods. Every year, thousands of lives are saved simply because satellites provide the early warning that ground-based systems could never deliver. Monitoring wildfires and volcano satellites are equally critical for wildfires. GOES and NOAA satellites can detect heat signatures before flames are visible from the ground. This allows firefighters to act quickly, containing fires before they spread. During the 2022 Tonga volcanic eruption, Himawari 8 captured breathtaking images of the explosion and the shockwaves spreading across the globe. Those observations were not just historic, they triggered tsunami warnings across the Pacific, protecting millions of coastal residents. Aviation and shipping safety. Imagine flying on an airplane across the Atlantic or Pacific. Pilots rely on satellite weather data to avoid dangerous turbulence, thunderstorms, or volcanic ash clouds. Without satellites, air travel would be far more dangerous. Ships crossing the oceans also depend on satellites to navigate storms and avoid severe weather conditions. Global commerce, the movement of goods across seas and skies, is safer and more reliable thanks to satellite data. Agriculture and food security. Weather satellites also play a vital role in agriculture. Farmers around the world depend on accurate forecasts for planting and harvesting. Satellites monitor rainfall patterns, drought conditions, and soil moisture, helping predict crop yields. In regions like Africa and South Asia, where millions rely on seasonal rains, satellite data is crucial for predicting droughts or floods. ensuring food security and guiding humanitarian aid, climate change and environmental monitoring beyond daily forecasts. Satellites help us understand long-term changes in our planet's climate. NOAA-20 tracks shrinking polar ice caps and shifting snow cover. Meteosat and Himawari provide long-term data sets for global warming research. Satellites monitor greenhouse gases, deforestation, and desertification, giving scientists the evidence needed to tackle climate change. Without weather satellites, our knowledge of climate change would be fragmented and incomplete. The forecast in your pocket hand. Finally, perhaps the most personal impact, the weather app on your phone. Every forecast, every rainfall prediction, every warning you see comes from satellite data processed by meteorological agencies. When you decide to carry an umbrella, cancel a picnic, or prepare for a storm, it's thanks to satellites orbiting high above, silently working to keep you informed. More than machines, weather satellites are not just tools of science. They are part of a global safety net that connects humanity. Whether you're a farmer in India, a fisherman in the Pacific, a pilot crossing the Atlantic, or a family in Florida preparing for a hurricane, satellites are watching, guiding, and protecting. They are proof of what humanity can achieve when science, technology, and international cooperation come together. We began our journey by asking a simple question. How do we know what tomorrow's weather will bring? The answer, as we've discovered, lies far above us, in the satellites that circle Earth, silently watching our skies. From the pioneering days of TIRAS-1 in 1960, to today's advanced fleets like GOES, Meteosat, Himawari, and NOAA. -20. Weather satellites have transformed forecasting from guesswork into science. They allow us to see storms before they strike, track hurricanes across oceans, monitor wildfires from space, and even study the long-term changes in our climate. These satellites are more than machines. They are lifelines. They save lives by providing early warnings. They protect economies by guiding aviation and shipping. They safeguard food supplies by monitoring rainfall and droughts. And they give scientists the data needed to fight climate change. They also represent something greater: international cooperation. Weather knows no borders, and satellites remind us that the challenges we face, storms, disasters, and climate change, are global challenges. The United States, Europe, Japan, and many other nations share their data freely, proving that when humanity works together, we are stronger. And perhaps most importantly, these satellites connect to each of us personally. The forecast you check on your phone each morning, that simple symbol of sunshine, rain, or snow, is the result of thousands of engineers, scientists, and satellites working tirelessly above our heads. As we look to the future, weather satellites will only become more powerful, with higher resolution, faster imaging, and smarter instruments, powered by artificial intelligence. They will help us prepare not just for tomorrow's storms, but for the challenges of an ever-changing planet. So the next time you step outside and feel the wind, the rain, or the warmth of the sun, remember that high above, satellites are watching, guiding, and protecting. They are our silent guardians in the sky.